Hi, my name is Sylvia Guarracino, and today I will be going into depth about the golden ratio specifically found in art. Before we begin, I wanted to list out what will be the structure of this video. So first, we will start with the basic information and concepts of the golden ratio. Then we will visit the timeline in which I will go into detail on the history of the golden ratio. Then we will get to the examples which demonstrates art that has used the golden ratio. And finally, we will discuss the Fibonacci sequence and its relationship to the golden ratio as well. So let's start with the basics. The golden ratio is a mathematical ratio that is approximately equal to 1.618, or 1 plus root 5 divided by 2. The actual number is 1.618033988749895, and it continues on without pattern. The golden ratio is denoted by the Greek letter phi. The golden ratio is essentially a ratio of a line segment that is cut into two pieces of different lengths such that the ratio of the whole segment to the longer segment is equal to the ratio of the longer segment to the shorter segment. This relationship continues repeatedly, and if getting larger, infinitely. In terms of present-day algebra, if the length of the shorter segment is 1 unit and the longer segment is a, we can get the equation a plus 1 divided by a equals a divided by 1, which mirrors the equation that's given in this chart over here, which can be rearranged to form the quadratic equation a to the power of 2 minus a minus 1 equals 0. The positive solution to this is a equals 1 plus root 5 divided by 2, which is the golden ratio. So now let's move on to the timeline. The timeline has been broken up into 6 major historical periods: the Egyptians and the Greeks, the Renaissance era, the 16th century, the 18th century, the 1900s, and modern discoveries. Let's start with the Egyptians and the Greeks. It is a possibility that the ancient Egyptians used both pi and phi to design the Great Pyramids. Phidias, who lived from 500 BC to 432 BC, is a Greek sculptor and a mathematician, studied phi and applied it to the design of sculptures for the Parthenon. Plato, circa 428 BC to 347 BC, and his views on natural science and cosmology presented in his Timaeus, considered the golden ratio to be the most binding of all mathematical relationships and the key to the physics of the cosmos. It was not known as the golden ratio in his time, but he described it with his first reference to proportion, in which he states the following: "Now it is not possible for two things to be combined well on their own without a third, for some bond is required between the two to draw them together. The very best bond is that which, as much as possible, makes itself and the conjoined entities one, and it is proportion that by nature best accomplishes this. So whenever the middle item of 3 numbers or volumes or powers is such that the first is to the middle as the middle is to the last, and again that the last is to the middle as the middle is to the first, then the middle becomes first and last and first for their part both become middles. Accordingly, it follows of necessity that they all turn out to be the same, and since they have all become the same as one another, they will all be one." This is analogous to what Euclid later wrote around 365 to 300 BC in Elements, in which he referred to dividing a line at 0.6180339 point as dividing a line in the extreme and mean ratio. This later gave rise to the use of the term mean in the golden mean. He also linked this number to a construction of a pentagram. The Greeks also referred to the golden ratio as dividing or sectioning property, but later shortened the phrase to the section. Now we move on to the Renaissance era. The golden ratio was first called the divine proportion in the 1500s by Leonardo da Vinci. Da Vinci had provided illustrations for a dissertation published by Luca Pacioli in 1509 titled De Divina Proportione, which contains drawings of the 5 Platonic solids. In his work, he talks about the proportion and the importance it presents in his pieces. Renaissance artists like Leo used the golden ratio extensively in their paintings and sculptures as well. Leo used it again in his painting of the Last Supper, from the dimensions of the tablet in which Christ and the disciples sat to the proportions of the walls and windows in the background. Later in the 1500s, Johannes Kepler, from 1571 to 1630, discoverer of the elliptical nature of the orbits of the planets around the sun, also made mention of the divine proportion, saying this about it. Geometry has two great treasures. One is the theorem of Pythagoras, and the other the division of a line into extreme and mean ratio. The first we may compare to the measure of gold. The second we may name a precious jewel. Moving on, the golden ratio was coined in the 1800s by Martin Ohm, circa 1792 to 1872, who is believed to be the first person to use the term golden to describe the golden ratio. In 1815, he published Die rein elementare Mathematik, the pure elementary mathematics, in which the book famously uses the term goldener Schnitt, which can be translated to golden selection. The term phi was not used to designate the golden ratio until the 1900s, when American mathematician Mark Barr used phi to symbolize the proportion. His reference appeared in Theodore Andrea Cook's book, The Curves of Life, which you can see is shown on the side here. Phi was chosen because by the 1900s, the universal proportion had many names, such as the golden mean, golden section, and golden ratio, as well as the divine proportion. However, there had yet to be a symbol connotation. Phi is the first letter of Phidias, who used the golden ratio in his sculptures. Phi is also the Greek equivalent to the letter F, which is the first letter of Fibonacci. Phi is also the 21st letter of the Greek alphabet, and 21 is one of the numbers in the Fibonacci sequences. Recent appearances of phi in math and physics appear in Roger Penrose's discovery in the 1970s Penrose tiles, which allowed surfaces to be tiled in fivefold symmetry, and it appeared again in the 1980s in quasi-crystals. So now we move on to the examples, and this was by far my favorite part of the research. So as you can see here, we have the Parthenon, which has been rumored to be used the golden ratio here. And then obviously Leonardo da Vinci was a master of the golden ratio. He used it in a majority of his artworks. Then we have Raphael Sanzio in the Madonna of the Goldfinch, circa 1505 to 1506. You have the Mona Lisa, which is a more famous painting, again, Leonardo da Vinci. We have Petrus Christus, a goldsmith, in his shop, circa 1449, which was an oil and oak panel. We have the Under the Wave of Canagua, also known as the Great Wave. We have Piet Mondrian, which was a more modern painting. We have Remembrant, the Anatomy Lesson of Dr. Nikolai Stulp. And then we have Johannes Vermeer, Girl with a Pearl Earring. Again, another iconic painting. Bringing it back to math, it's time to discuss why the Fibonacci sequence has been brought up so many times in this video, or why it has any correlation to the golden ratio at all. The Fibonacci sequence was written in India in about 200 to 300 BC and brought to the Western world around 1200 AD. What we now know as the Fibonacci sequence is named after Leonardo Pisano Bonacci, aka Bigoglio, of Pisa, an Italian born in 1175 AD, who later became known as Leonardo Fibonacci. His book Liber Abaci, published in 1202, introduced the sequence of Western European mathematics in the form of a math problem on the breeding of rabbits. He learned of it while being educated in North Africa with an master where he was exposed to the much earlier knowledge of Indian mathematics. Liber Abaci became a pivotal influence in adoption by the Europeans, which used the decimal system of counting over Roman numerals. The Fibonacci sequence first appears in the right margin of paper on the page in Liber Abaci, which is a copy of the book that is held by the Biblioteca Nazionale di Firenze. The sequence itself, though, had been described as early as the 2nd or 3rd century BC in the works of Acharya Pingala, an Indian mathematician who enumerated the possible patterns of Sanskrit poetry that could be formed from syllables of two lengths. The contributions of Pingala in Fibonacci are important, but it's not even apparent that anyone even realized its connection to the golden ratio until the 1600s by Johannes Kepler and others. The sequence itself can be explained as such. In the Fibonacci sequence starting with 0 and 1, each new number is simply the sum of the two before it. So if you look at the numbers below, such as 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and etc., you may not be able to see a clear pattern forming, but if you do out the math, it becomes increasingly obvious. This pattern can be expressed in the recursive equation written below, Fn equals Fn minus 1 plus Fn minus 2. The ratio of each of the successive pair of numbers in the sequence approximates phi 1.618. So for example, if you take 5 divided by 3, it would get 1.666, and if you take 8 divided by 5, you would get 1.60. Both of these numbers are very close to 1.618. In our homework question 536, we can see this pattern written out once again, each number being the sum of the two numbers before it. We even wrote down the ratio between each successive pair and expressed its relationship to the golden ratio here. In my own time, I attempted to see if my artwork held up against the golden ratio. And while I must admit that I am no Leonardo da Vinci, I do think my piece held up pretty well against the sectioning, especially the rectangular scale. Achieving proportionality harmony is definitely a lot easier said than done. That is all I have left for you guys today, and in the end I can confidently say that the golden ratio is one of the most important mathematical achievements in modern history. And I challenge you all to go out and try to use the golden ratio in your own artwork, or even find it in the world around you. Thank you so much for watching and have a great day. Bye!